My name is Ryan Smith, and you can find me on the internet at ryan.smith, places like GitHub, Twitter, etc. So I'm an engineer at Heroku, and I work on the API team, and I think a lot about databases and queuing and distributed systems and things like that. So I'm kind of going to flesh out some ideas that I've been thinking about over the past year today. So I also like fast-running programs, and I'm sure you guys do as well. And so, in this talk, I kind of want to flesh out a few ideas I have on how to make our programs run fast using some concurrent programming techniques. So some of the goals that I'd like to accomplish, with this talk, well, basically, I just want to answer some questions. And so one of the questions I want to answer is, how much concurrency do I need? Also, what can I trade for more concurrency? And what does concurrent code look like? So concurrent programming is kind of a beast. Like, I know such a very small subset of it. And so today, we're just going to cover just a small niche, and that's the niche that I've kind of been working in for a while. So let's get started, and let's try and tackle the first question. So how much concurrency do you need? And to think about this question, I think we should reason with some computer science to kind of discuss, what concurrency can do for a program. And so there's been actually a great deal of research in computer science regarding concurrent programming. One of the dudes who's pretty legit at concurrent programming is a guy named Gene Amdahl, and he came up with this interesting law that kind of talks about. Well, he set up like a kind of a framework that if we can figure out the ratio of concurrent code to non-concurrent code in a program, then we can kind of reason about how beneficial adding more processors to our program will be. So the law is stated as computations are limited by how much of the computation must be computed sequentially. So this is the mathematical expression that represents his law. So S here is a function of both P and N. So let's break this down. So S is the speed up of the computation. P here is the amount of our computation that can be parallelized, and N is the number of concurrent processors. So in the denominator to the left of the addition symbol, 1 minus P, that's like the representation of our non-parallel running code, right? And we can see that, if our code was 100% concurrent, that 1 minus 1 would be 0, and then it's just a function of our 1 over n, and as n goes to infinity, so does s. So in a perfect world, our speed up factor is linear with our number of processors. So let's kind of take this and plug in some numbers and see what happens. So let's say that we have a Ruby web application, and let's say that for any given web request, we have to call 10 methods to serve that request, right? Let's also say that 9 out of those 10 methods can be executed concurrently. So maybe there's one method call in our call stack that is non-concurrent. Perhaps it blocks on I/O. Perhaps it has to write. So there's that one method that's our bottleneck. And let's also say that we have 10 processes, right? So if, like on Heroku's platform, let's say you have 10 dynos, or you have 10 thin processes that's running your application, right? So if we simplify, we get this expression, and if you do the division here, you get a number that's really shocking, because remember, we have 10 processes, right? It should be fast. It should be a wonderful number, but in fact, it's only 5.2. So this is no good. We have 10 processors, but we only saw a speed up of 5. That's whack. So let's say that 10 wasn't even doing it for us, right? Like, we were just barely getting by on 10, and we need more performance. So the easy thing to do is just, well, we'll scale horizontally, right? We'll just add more nodes, and we'll see all this great performance, and it'll be wonderful. Well, okay, so let's add 20 workers, right? Well, given the law that we just stated, with 20 workers, we only see a speed up of 6.9. So this is a diminishing return. Like this is not good. So even though 90% of our code was concurrent, it's that last 10% that is really holding us back in terms of achieving overall performance. So to answer the question, how much concurrency do we need? Well, if we want to get the most bang for a buck, we need 100%. There's just no way around it. Your entire application must be concurrent to see good speed up factors. So where do we begin, right? This is, in my experience, getting from the 90% concurrency rate to the 100% is a very difficult challenge. And there's probably no one solution, to get you to that 100%. It probably depends upon your application. So I'm not going to present a general solution here. There's no silver bullet. But what I do want to do is I want to show you guys an application that I encountered a few months back where this was the case. And I just want to kind of walk through the steps that I took to get from that 90% to the 99%. I'm sure I didn't get all the way, but I want to kind of close the gap on that and show you guys what I did. So I had to write this program that was for our business intelligence team, and it was pretty crazy. We wanted to kind of report and predict some trends in our revenue for our Heroku customers, and so we estimated that we would have anywhere between, well, about 3 million jobs per day that we had to run. And to handle all this work, we figured that we needed probably about 100 workers. And we were also going to be using Postgres as our message queue to communicate, to dispatch all of our jobs. So, we prototyped the system, we tested it on some smaller data sets, and it was working well, it was correct. And so the time came where we were going to, ship it. We were going to do it live and put it on a real data set. And so, the day came for our maiden voyage, and we launched it. And then we started looking at our performance metrics, and we had set up some probes, and so we were kind of watching the progress of the program. And we saw that we had some real serious problems. Things were not going as expected. Like the program was just running really slow. We were quickly falling behind in terms of the backlog in our queue. So then we kind of had to take a step back and look at our application and try and figure out and try and reason why were we seeing this awful performance. So we looked at our application code. We looked at all of our business logic methods, and we kind of reasoned about could this be causing a bottleneck? We were asking these sorts of questions, and we were okay with all of our application code. It was very, for the most part, it wasn't too complex, and we were okay with it. And theoretically, it should have been able to run concurrently, right? So we kept on diving deeper into our stack, and the next place that we looked at was our message queue. So, and this is where we saw all sorts of problems. We were using some of Postgres's they have some connection monitoring tools, and I think it's called PG stat activity. But you can select PG stat activity, and it gives you all sorts of useful information about threads and who's blocked and who's waiting for I/O and stuff like that. But so we used those sorts of tools, and we determined that our message queue was totally being bogged down. In fact, we realized that even though we had 100 workers, only 30 of those workers were actually doing stuff. So we kind of paired up each worker with how many jobs that it worked, and we found that only 30 of them were only doing work. So 70 were just doing nothing. They were idle. They weren't accomplishing anything for us. So the majority of our scale was just sitting around. Our workers were unemployed. So this was very concerning to us, and so we kind of then took another step back and said, okay, well, why is this? How can we explain what is going on? So I thought about the problem for a while, and I kind of sketched up, what was my process? What did it look like? What was happening? And so I think I got it figured out. I think I realized why only a small subset of my workers were actually doing stuff. So consider the case here where we have n workers, right? In our case, it was 100. And each time that, well, let's just start from the beginning of the program. So we have 100 workers. They're just sitting there. The queue is empty, right? And then that one job, like the first job, gets put into the queue. Well, all of our workers, all 100 of them, are going to go storming to the queue, and they're going to try and get that first job, right? Well, there's only one job, so only one worker can get it. So that means 99 workers then all back off from the queue, and then they'll try again, right? And so you can imagine that this happens quite often, that you have a whole bunch of workers just backing off, then going to the queue, then backing off, and each time only one worker will be successful. So I think people call this a stampede. All of our processes are just stampeding, and they're moving back and forth, and there's a lot of motion going on, but no work is being done. And we couldn't prove this, but this was my hypothesis, and I think that at the time I was like, this has got to be what's going on. This has got to be the problem, and so then I set out to kind of solve this problem. We didn't have any concept of fairness amongst our workers, right? And so I think that's kind of what we wanted. We wanted a way to somehow allow more workers to get jobs. So then I started looking at the message queue, and I came to a point where I was like, all right, I have to trade something off to get better performance. I have to do something here. The current system wasn't working for me. So I started just listing off stuff, attributes of my message queue, trying to find out which component or which method was holding me back. So the first thing I did was I looked at my database, and I said, okay, is the database the best place to have a message queue? Should I be using AmpQ or Beanstalk or one of these highly available message queuing systems? And I kind of went down that road for a little while, and I started reading some papers on Postgres, and dang it, they've been working on this problem for 15 years. Tons of academia has gone into Postgres, and there's no reason why Postgres can't be this awesome concurrent data store. And also it has this good quality, which I really enjoy, especially when working with financial data. It's durable. I don't know if that means anything to you MongoDB people. We make a lot of jokes about Mongo. Actually, a funny one I heard the other day, we had a Mongo coffee cup in our office, and Blake Miserani picks it up and he goes, if they were really to design this coffee cup correctly, they should have drilled a small hole in the bottom. And so anyways, I like the acid quality that Postgres gives me, so I wanted that, and also introspection. So one of the when I kind of built this message queue for this application, I was really leveraging SQL to give me a status report on where my queue, what state was my queue in. I wanted to know, because it was definitely a heterogeneous queue. I had hundreds of different types of jobs in the queue, and so I wanted to get feedback on what sort of jobs were in the queue and what were their parameters, and I did all this reporting so that anybody could go into the system and quickly see what data is being worked on now. So that was very important to me. So these two kind of factors kind of kept me on the path of using Postgres as my message queue. So getting that, working through that, it left me with one other thing, and that is the queue itself, the abstract, the abstract notion of a queue, right? And then I got really deep, and I was like, well, what is a queue? I pondered, what is a queue? What does it mean? And a queue is just a list, right? And it has one fundamental attribute, and that is it provides you with a first in, first out guarantee, right? So first in, first out, that's all I know. And then so I started focusing on that. I was like, okay, first in, first out. Wait a minute, first in, first out? Like, this isn't what I wanted. Like, first is, it kind of implies one. It's like a unit. Like, I don't want one in and then one out. What I wanted was, I wanted many to go in and I wanted many to go out. I wanted my workers to be able to take out many jobs at one time, right? And not like, and that doesn't mean one job or one worker take many jobs, but that means many workers take, you know, one job at one. That's like, you know, it's a concurrent operation. I want many processes to take data out at the same time interval. So you might be thinking to yourself, well, gee, what good is a queue if it doesn't have first in, first out? And which is a perfectly reasonable question to ask. In fact, most of the dudes on my team were like, dude, you know, that's kind of crazy. Like, what are you thinking? And then so I came up with like a little bit of a thought experiment that helped me kind of reason through this idea. And so let's think about this scenario here. Okay, so we enqueue job 0. We put a job into our queue, right? Well, then we put another job into our queue, and this is job 1. And you can kind of think of these, like computer scientists would call these linearization points. And so this kind of helps us reason about concurrent processes. It's definitely a term to Google for. You'll find lots of good information out there on it. Okay, so we enqueue job 1. And then let's say sometime later, worker A takes job 0, right? Okay, then worker B takes job 1. Right, so now our queue is empty. Workers have the jobs. And let's also say that maybe the workers are on different machines, like worker A and worker B are on different networks even. So for whatever reason, you know, because of like a system backup or, you know, maybe a memory chip just died, worker A starts to slow down, and then worker B speeds up, right? So what happens then is worker B finishes job 1, and then worker A finishes job 0. So kind of the question that I'll throw out there then is like, you know, in this scenario, what good was first in, first out to us, right? And I'm sure we could all come up with like weird edge cases. Well, you know, I have this application that where jobs are dependent upon each other, and that may be, and so maybe you do need first in, first out, but I would say, you know, for my case in particular, and for many of the cases that I have seen, like I don't really need first in, first out. You know, I kind of need like a general concept of that, but I don't need like the granularity of one in and then one out in that specific order. So, you know, so this thought experiment kind of helped me steer away from this first in, first out constraint. So then, you know, what could I trade? You know, I kind of, you know, like, hey, computer science, what will you give me for first in, first out? Well, computer science gave me this concept of fuzzy first in, first out. And I started reading like a whole bunch of ACM digital library articles on this topic, and yeah, and there's all sorts of great research, and I encourage you guys to check out the digital library. It's got a lot of good stuff in there. But I found this guy who kind of who was using what he called rendezvous channels to kind of dispatch work to workers in a more concurrent fashion. And so I kind of adopted his idea and forked it and called it fuzzy first in, first out. And so yeah, so let's see what fuzzy first in, first out changes about our situation here. So instead of having like one head, we have many head nodes. And we block it off by specifying a top boundary. So in our queue, instead of having like a head, instead of always dequeuing that head, I'm kind of relaxing the constraint a bit, and I'm saying, okay, when a worker comes into the queue to take a job, they can take the head, but they can also take, like a relative head, right? So anything between, 0 and the top boundary, right? And the top boundary is tunable, and it should be specified by the person who's building the system. I think for 100 workers and the amount of jobs that we had, and they were short-lived jobs, I think we ended up going with 10. Like 10, a top boundary of 10 gave us like really good performance. I don't know why that is. I started with like 100, then went to 50, and I did like a binary search to find 10. But 11 might work for you. Okay, so we have this top boundary now where these workers are taking those 3 jobs all at the same time, right? So that's wonderful. Fuzzy first in, first out. So we've removed this constraint, right? Fewer constraints, more concurrency. Right, so now you're probably wondering, and rightfully so, what procedure can do this? What does the code look like to get us this, this concurrent system? So this procedure, that's the answer. So let's kind of just pick this apart. I call this operation lock head. This is like the function in my system that I use to accomplish all this. And so you might be curious about the implementation here. This is PL/PG/SQL. It's a procedural language, and it's a very interesting exercise to write programs in PL and PG/SQL. I encourage all of you to try. I don't know if there's like a tryplpgsql.com website, but seems to be popular. Okay, so let's walk through this. So what I'm doing here is I'm selecting ID from jobs. So jobs is a table that holds all my jobs. Where locked at is null. So this says that I want to take a job that hasn't already been locked. And I'm ordering by ID ascending. So this is an ID is like a serial integer. So this kind of gives me my order here. So the next thing I do is I limit it to 1. I only take one job at a time. And this next line is the fuzzy first in, first out line. So I ask for an offset, and I concat. So the 2 pipes are like a string concat. By the way, it's not like a Boolean operation. So I concat it with a relative top. And so I don't have the code for relative top, and that's because relative, like, you're computing the offset. So for me, like, my baby steps, like my V0 approach to computing a relative top was to just take a random number between 0 and my top boundary. So that means, any time that a worker would come in and try and select a job, it would compute an offset randomly, 0 in my top boundary. Now, there's all sorts of like great ways to optimize, this. Like I just did random at first, and actually I saw great like performance just by randomizing it. Like that gave me like good enough performance. But then I've also been thinking a lot about like, well, random seems kind of silly. Like I'm sure there's like a more solid approach to like, pairing up workers and jobs. So if you guys are curious, like find me today and we can talk about all sorts of crazy ways to compute relative tops. My wife doesn't want to hear about it anymore. So the next line that we state here is that we're going to select it for update. And so this is a nice like concurrent fundamental that Postgres gives us. And I heard my SQL got it recently too. It's called MVCC. And so basically what for update does is when we select that row and we have that tuple in memory, Postgres puts a lock on it, and so that if any other process tries and takes this row, like it will block. It'll just sit there and wait for that lock to be released before the other person can select it. So if you type select while somebody's updating, it'll just kind of hang and you won't be able to do anything. And so so the next line, I specify that I don't want to wait. So in the case that somebody else has already selected this row for update, and then I come in and select it, I do not want to wait, so don't lock me up. Just throw an exception, and I'll figure out how to handle it, and I'll just move on, right? And then I put all that into a locked variable so that I can do stuff with it later. So this is kind of the building block that I'll kind of abstract upon and kind of bring, so next we'll take a look at how this fits within our actual application. So, so in our Ruby code, like I use syntax like this. I say, a job is equal to a DQ on my queue. And so what that does is that will take like a Postgres connection, and also I want you guys to consider that maybe you're at like this Ruby code and this PL/PG/SQL, they're probably on different machines, and they could be on different networks, right? So when I call DQ, I'm like basically issuing a select statement. So I'm saying select lock head. I'm calling that lock head function. So I'm sending that message to a server, a database server, and so then in my SQL, or on my Postgres box, I say, so while attempts are less than n, and let me back up a bit. So this chunk of code here is another concurrent programming trick, and it's called a spin lock. And it's another wonderful term to Google. But basically what we're doing here is we have a resource that is locked, and we're going to spin a few times until the lock is free for us to take. So what we're doing here is we're saying while the attempts are in, or is less than n, and again, n is a very sensitive number to computer scientists. There's been tons of research on what's a good number to stop at, or should it be infinite. And anyway, so it's totally arbitrary though for me. So while we're spinning, call that lock head procedure. If we didn't get an exception, that means that no wait, it threw an exception if we weren't able to get it. So if we did get it, then we can break and return the job back to our Ruby process. So in the case that we did raise an exception because we didn't want to wait for the lock to be unlocked, then we just increment the attempts and then try again. So this means that our Ruby process can just say, hey, I need a job, and then it can go over the network, right? Because the cost to send that message to our Postgres instance is actually pretty expensive. It's a network round trip, right? We have to open connections, we have to send, we have to ACK, it's TCP. If there's bad network connections, it's gonna take a while. So it's nice to just kind of lob that message over to our server and then have our server kind of handle so if it didn't get a job, it'll try again on the server without having to go through the whole TCP connection business again. Okay, so then we finally got a job, right? And then so then it kicks it back to our Ruby process, and then we can actually work the job. So that was concurrent code, actually. It's not, it might not be the best concurrent code. It might not be crazy concurrent, but it is concurrent nevertheless. I want to go back actually and kind of just highlight some attributes that make it concurrent, just to kind of reiterate and talk about what it means for the code to be concurrent. So, and this is, and I'm just kind of explain how I think about this because it took me a while to get my head wrapped around, reasoning about concurrent code. So in this procedure right here, we say, and I want to focus on the lines for update and then no wait. So for update and no wait, those statements mean different things to different processes, right? You can't think about this block of code in terms of just one process, right? Because we're hoping that it's concurrent. So we're going to have many processes who are in different states executing this code. So for the first person that came in, or for the first process that came in to this chunk of code, for update, no wait, doesn't mean anything to them, right? Because they've probably already got the lock, they've already got the job, and it's done. However, for anybody else who comes in during that time, for wait, for update, no wait means very much to them. It's a fundamental part of our algorithm. So that's kind of the idea behind concurrent code, is that there's going to be weird stuff that that doesn't apply to all your processes, but it applies to some of them. So this code doesn't mean everything to everyone all the time, but it does mean something for a few people, or a few processes. I call processes people. I don't know why. This guy locked the job or whatever. I don't know. Cool. So that was concurrent code. And so in terms of the goals that I kind of set out to accomplish, I hope I've shown you guys how much concurrency you need, right? With Amdahl's law, we need 100%. If you're not writing 100% concurrent code, then you're fired. So what can we trade for more concurrency? Well, we gave up first in, first out, right? We gave up a fundamental concept of our system. Or it was fundamental and we thought we needed it, but really we didn't. So I think so when you're approaching programs that need to be executed in concurrency and they need to be run in parallel, you're probably going to have to relax some of your constraints, and you have to rethink your problems. Your fundamentals that you had going into the problem are probably going to change once you try and make it more concurrent. And what does concurrent code look like? Well, that SQL is pretty gnarly, but it's just you basically have to reason about your chunks of code with respect to different processes which are in different states. And so finally, if you're curious at all about some of the concepts that I talked about in my queuing situation, I've kind of wrapped all that together and put it into a queuing library called QClassic. And so if you're interested in using this type of system in your own application, I encourage you to at least follow the project and perhaps even use it. Yeah, so that's what I've got, and I'd like to open it up for discussion now. So any questions? Yes. Oh, sure. So the question was, what sort of dependencies does QClassic have, specifically with respect to delayed job? And so QClassic, I don't even use bundler. Oh my gosh. Because I have 2 dependencies, and the dependencies are PG, the PG gem, and JSON. And so QClassic is really fast because I wrote all the SQL myself. Again, oh my gosh, writing SQL. And also I don't create very many Ruby objects. And that's how I found, like whenever I go to optimize Ruby, I stop using all the gems and I write Ruby code. And I try and keep it as small as possible. And so I hope that answered the question. Skip lock. So he asked, instead of for wait, have I used skip lock? And no, I haven't, because I just found out that it existed in Postgres a few weeks ago. I know that Oracle has had it for a long time, and that's one thing that I've always been jealous of. But skip lock is definitely, I think, a better approach. So I'm glad you brought that up. So add that to your Google list. So I didn't care about the order, right? And so you're asking, like, why don't I care about the order? And that's because, so for this particular case, like I had, I thought of a job in terms of a customer, right? And I thought of that job I thought of that customer with respect to time. So I said, okay, I have 1,000 customers that I need to compute some data for a given time. So what is it like? And so what does it matter if I start working on customer 1 or customer 2, right? It doesn't matter. Like I have to get a whole bunch of customers done at one time. So it doesn't really matter to me whether I start with customer 1 and then go to customer 2. Like for that particular case, it did not matter. Like if I would have done customer 2 instead of customer 1, I would have gotten the same result, right? So that's so that's the specifics of the application that allowed me to not care about the order. Now, so I would enqueue 1,000 customer jobs at a time, and then after that chunk of jobs, I would enqueue another chunk of jobs, and it would be for the same customer but for a different time, right? So I cared about the ordering on a scale of on an order of magnitude of 1,000, but for on an order of magnitude of 10, I didn't care.
Hey Ryan, I'm going to exploit the fact that I have a mic also.
Okay.
Just as an add-on to that, so at Profitably where I work, we do a lot of background queuing, and we have to deal with a lot of complexity. And I have found basically, queue ordering is nice in terms of priority, as in this job came in, so this person deserves to get this work done before. But if you make it so that logically one job in the queue has to happen before another job in the queue, your life gets much, much harder. So
job dependency is a nasty road.
So
Don't
really
dragons be there.
Right. So
yeah.
What we do is, and there's a lot of ways to do it, and none of them are really clean, but what we do is basically when a job is done, it's responsible for firing off other things that were logically waiting for it to finish. Mm-hmm. Because there are totally times when you want to be able to say, oh crap, this thing happened, I need to be able to slam the jobs down or up in priority and slide them around. So.
Absolutely, yeah, he made a great point. I often have what I call fan-out jobs. So maybe I'll enqueue a job that does some work, and then the very last thing I do in that job is I enqueue 10 other jobs. It's also a great way. And that's a handy trick for even so for instance, when I enqueue those 1,000 jobs, I don't do all that in memory. I put that into a job, right? So I create a job to make 1,000 jobs. So I enqueue that one job, and that one job will create a whole bunch of other jobs. And right. So that's a very good solution. Is if you have that sort of dependency amongst your jobs, then let the job enqueue the job or let the dependent job depend upon. Yeah. Whatever. Yes. Okay. So there's 2 concepts of locking in this code right here. You'll see that first I'm selecting jobs that were locked out as null. And then there's also the for wait or the for update no wait, right? So when a worker takes a job, it's going to write a timestamp to that locked at, and so that way we're saying to the system, hey, like a worker has this job and they're working on, like the job has already been assigned, right? And so, so once you have that, then the worker is responsible for actually deleting the job. So does that kind of make sense?
Yeah, that's pretty doable.
So his comment was, why don't you have like the queue tell the workers what to work on? And I thought of that, and actually, so as a quick aside, QClassic, my library, I use, Postgres has a pub/sub feature that is wonderful to use, and I'm actually using it here, and you can actually communicate to processes using channels. And so I've even thought about that. I thought, well, maybe my queuing system could be smart, and it can just, when a worker comes online, then I can just, I can know whether it's busy, and then when I get a job, I can just kind of alert it. But then, and this is probably because, or maybe my coding skills weren't up to par at the time, but it was very hard for me. Like my code became very complex when I started figuring out how my queue should send jobs. Like my queue had to become smart. Like it had to become really, I had to teach it all these new things, and it got too complex, and so I stopped going down that route. And I can't, just even talking about it, it's kind of a difficult subject to talk about, you have to have this central server that communicates with other processes, and that doesn't sound like Postgres anymore. That sounds like something else, right? I don't think Postgres was designed to do that sort of stuff, so that's kind of why I stopped thinking about it. So maybe that, we can talk more about this later, but it seems like a good idea. Why do we need a top boundary? So I answered a question previously that asked about ordering, and I said that I had maybe batches of jobs, so I had 1,000 of this type and 1,000 of the other type. So I wanted to kind of constrain it just a little bit. So the question was if your worker dies and crashes, then they don't live long enough to delete the job or finish the job. So in that case, you have a stale job in your queue, right? You're going to have this, you might finish a long-range operation and there still might be 12 items in your queue, and they've been going for 20 hours, and odds are the workers, died. And this is I think this is a very hard problem to solve in a distributed environment, but so I've chosen not to solve it, but I've thought of ways that you could. And I know that using the PG stat activity table in Postgres, you can find out what workers are online. And so I thought about keeping another table so that when a worker takes a job, we put a record in this meta table, and then at any given time we can take an intersection of the PG stat activity with this logs table and determine which worker is not online anymore, and then we can go and do something with that job. So if you're interested in doing this, I think I'm probably going to be working on this in the next few weeks. So feel free, we can talk about it and come up with different designs. I would love to do that. So I computed a random offset because I couldn't there was no easy way that I thought of to compute a deterministic offset, and so so you can't so if it wasn't random, what would it be, right? If you specified a top boundary of 10, what would it be? Would you increment? Would you just say each worker that comes online takes the last offset plus 1? And if that's the case, how do you determine what the last offset was? So they can't keep looking until they find one. So we still have, because of the top boundary, I still believe we have to compute an offset, right? And so yes, they keep looking until they find one. That was the spin lock that I showed. That was kind of the idea there, is that I would try random spots, right, in the boundary until I found one. But so I still used the random function to pick out where I was going to look, right? I guess I could just go in order. Well, could I? But it's hard because each time that you try and select it, how do you have to keep a counter somewhere? Do you have to manage memory? Whenever I think about managing memory in a distributed environment, I always kind of back off and try and figure out a different way. That's a good question. I'm sorry I don't have a better answer.
Well, certainly there will be a lot of chance to follow up on that.
Okay.
But that's all the time we have for Ryan. Thank you very much.
Right on. Thanks.